We will continue with our treatment of transient conduction in this part of the class. What we have discussed previously is that in transient conduction, the temperature of a solid object can be a function of the space coordinates, for example x, y and z, and it is also a function of the time. So, when you have a hot solid object being cooled in a stream of cold air, depending on the dimensions, properties and other conditions of the solid block, the temperature inside the block can be a function of x, y and z. And since with time it is going to get cooled, it is going to be a function of time as well. Handling a situation in which the dependent variable, which is temperature in this case, is a function of 3 space coordinates as well as time, is difficult, and it would give rise to a partial differential equation which would require special techniques for their solution. However, one can make an assumption which would simplify the problem significantly, and one of those assumptions which I have mentioned in the last class is, if we assume that the temperature in the solid object is a function only of time, but it is not a function of the space coordinates, then what we would get out of the physical statement of the problem is an ordinary differential equation, which then can be solved using appropriate boundary conditions, and you would get the temperature profile, the temperature variation of the solid as a function of time only. So, that is what we have done we have started in the previous class, our introduction to transient conduction. The reason that I have included introduction of transient conduction in this course is to show you how the physical concepts can be used in modeling a process which would play a major role in all our future development of model equations of a system of which we would like to express the physics in terms of our differential equation. So, here we have the case of a transient conduction in which there is a liquid whose temperature is T infinity, and the temperature of the object initially T I is greater than T infinity. So, this is essentially a quenching process in which the temperature of the object would change with time, would reduce with time because of convective heat transfer from the walls of the solid to the liquid. So, the temperature inside the solid is going to be a function only of time if we assume that lumped capacitance model is valid. So, if the lumped capacitance model is valid, then the temperature is a function of time, but it is not a function of the space coordinates, for example, x, y, z, r theta phi or r theta and z, depending on the coordinate system that we are using. If we write the governing equation, E dot, that is the rate of energy in minus rate of energy out plus any generation in the system must be equal to the energy stored in the control volume. However, in this case there is no energy which comes into the control volume since its temperature is higher than that of the surrounding fluid. So, energy will go out of this solid object through a convection process. So, I have written the convection process in terms of a convective heat transfer coefficient, the surface area which is interacting with the liquid, the temperature at any given instant, and T infinity is the temperature of the fluid which is far from the solid. And we would also assume that the thermal capacity of the liquid or the amount of liquid is really large, and therefore, quenching one solid particle or a solid sphere would not alter the temperature of the liquid. So, T infinity is essentially a constant which does not vary with time. So, this is going to be the energy out of this. and there is no generation. So, as a result of the energy leaving the solid object, the thermal energy storage term will also change with time. So, the amount of energy change, stored energy change inside the control volume would be simply m rho times V C, which is the thermal which is the heat capacity of the solid material, times change in temperature with time. So, if I define a dimensionless temperature as T minus T infinity, then this equation would simply reduce to rho V C by H A S. Now, if you see this rho V C, it is some sort of a thermal capacity of the system. Rho times V is mass, mass times heat capacity. So, this is the thermal capacity of the solid in terms of the temperature, in terms of the energy that it can store, whereas 1 by H A S, 1 by H A S is the resistance, because from Newton's law we know that Q is equal to H A times delta T, and therefore, delta T is equal to Q by H A, or I would rather say I would express it as Q is equal to delta T by 1 by H A. So, this is the effect, the heat flow, and this is the cause. So, if I express Q as delta T by 1 by H A, so this can be termed as delta T by resistance due to convection. So, the 1 by H A, 1 by H A S, where A S denotes the surface area, 1 by H A S is some sort of a resistance to heat transfer, convective heat transfer. So, therefore, if you look at this system, I have a capacity term and a resistance term, and the differential equation that relates the change in temperature with time, this theta is defined simply as T minus T infinity in this specific form if I use the lumped capacitance model. So, when I use this lumped capacitance model, the question would obviously come is when we can say that the lumped capacitance model is valid. What exactly happens in the case of lumped capacitance, or when it would be prudent to use the lumped capacitance model? In order to address this question, what we have done is I am looking into the validity of the LC model, the lumped capacitance model, and I think this, let us say this is a solid object which is in contact with a liquid. The temperature of the solid at x equal to 0 at this location is arbitrarily denoted by Ts1, whereas the temperature at the other end of the solid which is in contact with the liquid is Ts2, and the temperature of the liquid far from the solid wall is T infinity. There is a flow of a fluid past the solid object which would carry heat away from the solid because of convection. So, this boundary x equals L boundary of the solid is experiencing a convective heat transfer process due to its interaction with a fluid whose temperature is T infinity, and the flow of the liquid maintains a heat transfer coefficient, convective heat transfer coefficient denoted by H. And it is further assumed that Ts1, the temperature at this location, is more than Ts2, the temperature at the interface, and it is greater than T infinity. So, of course, the heat is going to flow from x equals 0 to x equals L, and then by convection to beyond. So, if I do the surface energy balance at x equals L, so what I can say is that at steady state, the amount of heat which comes from the location x equals 0 at a temperature Ts1 to a location x equal to L, which could be at a temperature of Ts2, in the conductive flow of heat would simply be K times A, which is the cross sectional area. L is the distance between these two, Ts1 minus Ts2. So, Ts1 minus Ts2 divided by L essentially gives you the temperature gradient. The temperature gradient multiplied by the thermal conductivity and A would give you the heat flow from x equals 0 to x equals L. At the other side of the interface, this heat is going to be convected out by the Newton's law of cooling, where H is the convective heat transfer coefficient, and this should be T infinity, and this temperature is going to be equal to T infinity, Ts2 minus T infinity. So, if I take the ratio of these temperature drops, I can write Ts1 minus Ts2 divided by Ts2 minus T infinity is equal to L by Ka and 1 by Ha. If you recall your from your studies of conductive heat transfer, you know that L by Ka is simply the conduction resistance, the resistance due to conduction, and I have just described that 1 by Ha is nothing but the resistance due to convection. And if you simplify this, it is going to be equal to HL by K, where H is the convective heat transfer coefficient, L is the length scale, L is the length of the solid object, and K is the thermal conductivity of the solid, and this is defined as Biot number, and the Biot number is a dimensionless number, is expressed as Bi. So, HL by K is termed as Biot number. So, therefore, you can see, in order to have less temperature gradient in the solid, that is between x equals 0 and x equals L, the value of the Biot number must be small. So, if your conduction resistance is quite small in comparison with the convective resistance, the resistance due to the resistance to convection, then your temperature drop in the solid Ts1 minus Ts2 is going to be small. In order for LC model to be valid, you would like this to be small, the temperature drop in the solid. So, for validation of LC, therefore, in order for LC to be valid, your HL by K should be small. So, a small value of Biot number essentially tells us that we can simplify the system using the lumped capacitance model. So, Biot number is therefore an indicator, that is, Biot number has to be quite small in comparison to 1, and the small value of Biot number is an indication of whether or not we can use lumped capacitance model. Normally, the Biot number which is defined as HL by K, and this L I would now substitute with LC. So, LC is nothing but the characteristic length. Characteristic length of the solid. So, this Biot number should be less than 0.1. So, experimental values suggest that one can safely use lumped capacitance model if the Biot number based on the combination of convective heat transfer coefficient, the characteristic length of the system, and K, the thermal conductivity of the solid, is less than 0.1. So, while trying to solve any transient conduction problem, the first thing one should do is to check what is the value of the Biot number. If it is less than 0.1, then the variation of temperature inside the solid object, or the spatial distribution of temperature inside the solid, can be neglected, and therefore, at any instant of time, the solid can be treated as space-wise isothermal. At every point, the temperature would be the same if I fix the time. But obviously, with time, the temperature of the solid will change, and depending on whether or not it is exposed to a hot environment or a cooler environment, the temperature may reduce or may increase. However, it will remain space-wise isothermal as long as Biot number is less than 0.1. Now, again, from your studies of heat transfer, you probably have seen a dimensionless number which is HL by K. Normally, HL by K, we term it, the more common one is the Nusselt number. So, what is the difference between Nusselt number, which is also expressed by HL by K, and Biot number, again expressed as HL by K? The difference between the two is that for Nusselt number, the K that you have in the denominator of the expression refers to that of the fluid, whereas in Biot number, the K that you have is the thermal conductivity of the solid. So, depending on what you use, whether it is the thermal conductivity of the solid or the thermal conductivity of the surrounding liquid, you either have Biot number or you have Nusselt number. But Biot number therefore plays a very important role in transient conduction, and the value of which would let you know whether or not lumped capacitance model is valid and can be used. Now, when we talk about this characteristic length, if I expand this characteristic length a little bit more, how do I know what is the characteristic length? Generally, the characteristic length LC is defined as the volume divided by AS, where this V is the volume of the solid and AS is the surface area. Therefore, a simple geometry would tell you that for a plane wall of thickness 2L, with convection from both sides, the figure that I have drawn initially from both sides. So, you have a system like this, the total thickness of this solid is 2L, and you have convection here as well as here. This LC will turn out to be equal to L, where L is simply the half of thickness. And if you take a long cylinder, this LC would turn out to be R0 by 2, where R0 is the radius of the cylinder, and for the case of a sphere, this LC is going to be equal to R0 by 3. So, by definition, one should choose the characteristic length while calculating the Biot number for a system. The length, the Biot number defined as HLC by K, this LC should be this. But the common practice is to make your calculation, to make your assumption more conservative. The length scale is chosen, the length across which the maximum temperature difference takes place. So, this is a conservative estimate of what would be the characteristic length. So, therefore, you can see the maximum temperature difference takes place over L, and therefore, this is correct. So, for a plane wall we can take LC equals L, but if you think of a long cylinder, the maximum temperature difference would take place between the center line and the outside. Therefore, for this case LC for a cylinder, the conservative estimate would take the LC to be equal to R 0, and similarly LC for a sphere, a spherical system, is taken to be equal R 0 again. So, though the mathematical definition of LC is this, the conservative estimate for to calculate Biot number is taken in this. This is the dimension across which you get maximum temperature difference. Now, I go back to this formulation where we know that rho V C, this is the governing equation which we have written. This is essentially E dot out is equal to E dot stored, and you get this expression. So, if you integrate this expression, what you would get is simply rho V C by H A S integration from theta I to theta d theta by theta is equal to 0 to t dt. Remember that theta has been defined as t minus t infinity. So, when you integrate this, what you would get is rho V C by H A S ln theta I by theta is equal to time. So, therefore, theta by theta I would be equal to t minus t infinity divided by T I, which is the initial temperature of the solid before it is exposed to the convection environment, is equal to exponential H A S by rho V C minus H A S rho V C times T. Okay. And looking at, so therefore, the temperature of the object would change in an exponential fashion with time, and the time constant of the process is simply inverse of what I have written inside the bracket. So, this is the convective heat transfer coefficient, this is the surface area, rho, volume, and the heat capacity. So, the thermal, so the time constant of the process can be written as 1 by H A S times rho V C, and as I mentioned before, 1 by H A S is the resistance due to conduction, and rho V C is some sort of a thermal capacitance of the system. So, the thermal constant of the process of quenching or of the process of changing the temperature of a solid when it is exposed to a convection environment would this thermal constant would depend on the resistance to convection and the thermal capacity of the system. So, the behavior of the variation of temperature with time is analogous to the voltage decay that occurs when a capacitor is discharged through a resistor in an electrical circuit. So, of course, the higher the value of tau, the system will respond slowly in terms of the change in temperature with time. But this gives you a very simple way to treat the conduction in solid, the transient conduction in solid, provided you can use the lumped capacitance model. So, next we will quickly see how how this constant, the tau t that I have referred to in terms of H A S by rho V, how it can be combined to give you some more insight into the process. So, I am going to start with the expression for tau t, which is 1 by H A S times rho V C, and therefore, this can be written and I also have the time present in here. So, I am talking about the entire thing inside the exponential sign, which can be expressed as H L C, I am sorry, the reverse way, H A S by rho V C times T. This can be written as H, bring in a length scale by K, then K by rho C and T by L C square. So, the purpose of my doing this is to bring in the concept of Biot number. So, I brought in an L C and I put an LC over here, and this essentially are the same. So, this is the Biot number, and what I have over here is K by rho C is the thermal diffusivity of the system. I have a T and L C square. So, if I rearrange the terms, what I would get is H L C by K. You remember that V by A is the characteristic length of the system, which I have plugged in here, and since I have added an LC, here I have LC square. So, A by V, or rather V by A in here is substituted by LC. So, I have HLC by rho times T. So, HLC H times rho LC. So, I brought in another LC over there, and I have this formula. If this is dimensionless, this number which contains time must also be dimensionless. So, this dimensionless number is called Fourier number and expressed by this FO. So, this is Fourier number. So, the change in temperature of the solid object as a result in convection outside and conduction inside, and if lumped capacitance model is valid, is expressed in terms of two dimensionless quantities. One is a Biot number and the other is a Fourier number. So, the Fourier number compares a characteristic where Fourier number is alpha T by L C square. So, the Fourier number compares a characteristic body dimension with an appropriate temperature wave that penetrates. So, it gives you the how fast the temperature wave will penetrate into the depths of the solid. So, this more or less completes our treatment of LC, or our treatment of transient conduction, which is required in transport phenomena. But there is one thing which I would very quickly touch upon in 2-3 minutes, is there would be conditions in which the lumped capacitance model validation statement, that is Biot number has to be less than 0.1, will not be met. So, if Biot number is greater than 0.1, then there is no straightforward way to calculate what is the temperature. So, you have to write the equation will become partial differential equation, and you have to solve it numerically. Fortunately for practicing engineers, the solutions of transient cases when the Biot number is greater than 0.1 is available in all textbooks of heat transfer in the form of charts, which are called Hessler charts. So, if you look at Hessler charts, you would be able to find out, looking at the Hessler chart, looking at the knowing the dimensions of the system, the properties of the system, the convection environment and so on, you would be able to obtain what is the surface temperature, what is the center line temperature, how much heat is lost in a given amount of time, and so on. So, Hessler charts, I would write it over here. The Hessler charts, these are for the case when Biot number is greater than 0.1, they are available, and essentially what it looks like is theta naught, that is at 0th time, by theta I as a function of Fourier number. This is between 0 to 1, and you get a family of curves like this for different values of k by h l, and similarly you get theta by theta 0 as a function of k by h l. So, these are x by L to be equal to, let us say 0.2 to x by L to be equal to 1. So, knowing the Fourier number, you would be able to, where theta is defined as temperature as a function of space and time minus T infinity, or R and T minus T infinity. Theta I is the initial difference in temperature, and theta 0 is the center line temperature minus T infinity. Now, you understand, we realize that T 0 is essentially a function of time. This is the temperature, the central line temperature, how it varies. So, theta 0 is going to be a function of time. So, therefore, Fourier number contains time, since it is equal to alpha t by LC square. We know what is LC. So, at different values of time, I can calculate what is the Fourier number, and I go corresponding to this k by HL, the numbers of which are known to me, and I come over here and I get the value of theta naught, which is T 0 minus T infinity. So, this first curve gives me the temperature of the center line of the object as a function of time. So, once I find out what is theta 0 at a given time, then I come to this second curve. The second curve gives me theta, which is temperature at any location, divided by the temperature of the center line as a function of k by HL. Since k by HL is known to me, I read that value, I evaluate that value and go to the point corresponding to the x that I desire. So, let us say I desire x at this point, and then come to this side to find out what is the value of theta by theta naught. Since theta naught is known to me, I would be able to, theta naught is known to me from the first figure, I would be able to obtain what is theta, that means what is t as a function of both x and time. So, the first curve 1 gives me center line temperature as function of time. The second curve gives me temperature at any location and at any point of time as a function of theta naught, that is at a function of the central line temperature. So, the first curve, since I know that if at any given point of time, at any combination, the value of this combination gives me the central line temperature. The second one, these lines are for different locations. At the desired location, what is the value of theta, that is the temperature, as a function of the central line temperature. So, this combination, using these combinations together, these two graphs together, I would be able to find out what is the temperature of a solid object at a given location and at a given time. Remember, the Hessler chart is only used when the Biot number is greater than 0.1 and lumped capacitance model cannot be used. But in many of the practical cases, you would be able to use Biot number less than 0.1 and use LC and obtain an ordinary differential equation, which you can then integrate in order to obtain the temperature as a function of time. The space does not appear there, since it is space wise isothermal as per the lumped capacitance model. So, Biot number less than 0.1 and Biot number is k L by H. So, Biot number would be small if k is, if the Biot number would be, you have to look at the values, the value of the Biot number, which is H L by k. Biot number is H L by k. So, in order for Biot number to be small, the value of H has to be small, the length has to be small, or the thermal conductivity has to be large. So, these situations arise if it is open to natural convection, if the length scale is too small, or if you are working with a material that has a very high thermal conductivity. So, this property combination and the geometric observation, geometric parameter would give you the value of Biot number. So, that is more or less that I wanted to cover in the transient conduction problem. We would solve one problem on this in the next class, just to give you an idea of how to model a process, in which the temperature is changing with time, and this would be a useful exercise to know more about modeling the transport processes around a solid sphere which is losing heat to the surrounding fluid.